We have a couple different ways of finding the volume of regions after you rotate them around an axis. And it can be kind of tricky to know in any given situation if it's better to use one technique or the other. Is it better to use washers or is it better to use shells? So let's look at a couple examples where we'll think about that question and set up the corresponding integrals. We won't actually evaluate these integrals, but let's set them up just to see how it works out. So let's start out with this one. So we'll rotate the region enclosed by the square root function, y equals 0 and x equals 1, about the line x equals minus 1. So let's draw a picture of that just to see what it looks like. So x equals minus 1 is the axis that we're going to rotate around. And the square root function looks like this. And plus 1, say, is here. Drawing things not all to scale this time. Let me see if I can get these to look somewhat the same. So there we go. That looks a little bit better. Okay, so we're rotating around x equals minus 1. Now, if you're thinking about washers or shells, there's sort of a rule of thumb that goes along with this. So washers and shells will have different variables for the independent variable. And how it works is this. So if your independent variable is parallel to your axis of rotation, right? So in this situation, the independent variable that's parallel to the axis of rotation, that's the y-axis that's parallel to the axis of rotation. So if your independent variable is y, you get this cross-section for a y value. And then when you rotate this cross-section, what you get is a washer, like this. So if your independent variable is parallel to the axis of rotation, then you get washers. Or disks, maybe. Okay, but if your independent variable is perpendicular to the axis of rotation, in this case, the coordinate axis that's perpendicular to the axis of rotation is the x-axis. So we would get one cross-section for every x value. The line segment that is the cross-section of the region would be this blue segment. And when you rotate this blue segment about the axis of rotation, we get this cylindrical shell. So when your independent variable is perpendicular to the axis of rotation, you get shells. Okay, and these two rules of thumb, these are always going to be the case. So what we need to do in any particular situation is just ask ourselves, which way is nicer? As we imagine tracing the vertical cross sections from left to right like this, or the horizontal cross sections from bottom to top like this, are there any tricky situations we run into? By tricky situation, I mean maybe the end point of a cross section jumping from one function to another, or getting split in half, or something like that. In this situation, there's nothing tricky that happens for either way of slicing this up, so we should be able to write a volume integral for this shape using either washers or shells. So let's do it both, I guess, just to see how it works out. So let's do in the y direction first. So since the y direction is parallel to our axis of rotation, that's going to be washers. Each of these horizontal cross sections is going to rotate to give us a washer. Our y coordinates are going to go from down here, which is 0, to up here. This is the intersection point of the square root of x and x equals 1. Well, if x is 1, then y is also 1. So this top y value here is y equals 1. So for our washers integral, we're going to go from 0 to 1. And then we integrate the area of one of these washers, which is pi times the inside radius squared minus the outside radius squared. So that, I'm sorry, that's backwards. The outside radius squared minus the inside radius squared. So the outside radius, looking at this red washer, the outside radius goes from, let me use green, I guess. The outside radius goes from the axis of rotation over to this outside position here. Well, this outside position is always at x equals 1. And the axis of rotation is at minus 1. And so the distance from minus 1 to 1 is 2. So the outside radius is always 2. So that's squared minus, and now we need the inside radius. So the inside radius is, I don't know what color to use. This picture is getting a little cluttered. The inside radius is from the axis of rotation to, well, to the graph of the function, whatever that is. Right? And our function is right here. But for this integral, I'm sorry, I wrote an x here, but this integral is with respect to y. So we need to use y as an independent variable for this equation. In other words, we should solve this for x. So this is, right, to square both sides, it says x is y squared. Okay, so the inside radius is from y squared over to the x-coordinate minus 1. So y squared minus negative 1, which is plus 1. So this is our inside radius, so we need to square that. So this is our washer-style integral for the volume that we get by rotating this region. Now let's do a shell-style integral. So for shells, we're going to integrate from our inside x value, which is 0, to our outside x value, which is 1, dx, and it is dx this time, because to get shells, our independent variable has to be perpendicular to the axis of rotation. So that's the x direction that's perpendicular to our axis of rotation. And so we're going to integrate 2 times pi times the radius. And the radius is from the axis of rotation over to the position of the shell that we're at. So the axis of rotation is at x equals minus 1. Our position is x. So big x value minus small x value, that's x minus negative 1. So that's x plus 1. And then times the height of one of these things. That's the height of this blue line segment right here. And that's just given by the function. Well, this equation tells us the function. But since this is an x integral, we have to have y in terms of x. So we're going to use this one, y equals square root of x. So the height is just square root of x. All right. So if you needed to know the volume of the shape that you get by rotating this shape around the line x equals minus 1, you could use either one of these integrals. Both of them would give you the same result. I think for this example, it's really just a matter of taste of which one you think is easier. I think maybe the first one, the washer integral, might be a little harder to multiply out, but the antiderivative will be easier. And for the shell integral, it might be a little easier to multiply it out, but because of the square root, some of the antiderivatives will be a little bit messier. But it's really a matter of taste. Both of them will give you the same result. All right, let's look at another example. Let's rotate the region enclosed by y equals x and this crazy function, 2x over 1 plus x cubed, about the line x equals minus 2. And let's decide if we should use washers or shells. So this function, it's not, I mean, probably off the top of your head, you don't know what this looks like, and I wouldn't either, but I have it graphed on GeoGebra here. So the line y equals x is the black line, the black diagonal line here, and this green curve right here is the function that we're talking about. So we want the region enclosed by the two. That's this sort of diagonal wedge shape like this. So let's draw a picture of that. So x equals minus 2 is our axis of rotation. This wedge shape goes up to x equals 1, it looks like. So like this. To check that this really does go up to x equals 1, we should find the intersection of these two, right, just by setting them equals. So we should set x equal to 2x over 1 plus x cubed, and we should solve that equation. But just for now, let's assume that you do get x equals 1. You'd also get x equals 0. And it's possible there would be other x values, but these are the two that we want. So let's just stick with those two. And now let's imagine the two ways that we could slice this up into pieces. We could use y as our independent variable, in which case we get horizontal line segments. And because our axis of rotation is vertical, these will trace out washers. Or we could use x as our independent variable. In that case, we get vertical line segments. And in that case, when those rotate around the axis of rotation, we would get shells. Okay, so what are the things that we have to figure out for each type of integral? Well, if we use y as our independent variable, we're going to have to go from y equals 0, which is fine, up to the highest point in this region, which is right here. And we don't know how high that is. That would be the maximum value of this function from 0 to 1. And finding maximum values of a function can be pretty tricky. So that sounds like a lot of work. Also, to write the washer integral, if we're using y as our independent variable, then we need to solve these equations for x, so that everything is in terms of y. Well, this first equation, we do have x in terms of y. But for the second equation, solving this for x would be really difficult. That looks extremely unpleasant to me. So I would really not want to solve this equation for x. And if we aren't willing to solve this equation for x, that means that we cannot write a washer integral for this region. So we're stuck using shells. So hopefully shells will work. So what would we need to do to write the shell integral for this region? Well, we would need to integrate over all of the x values that touch this region, and the furthest left x value is 0, so bottom bound is 0, and the furthest right x value that touches this region is 1, so our top bound is 1. Already things are looking nicer than the washer integral because, right, we didn't have to find some weird maximum value. So continuing with the shell integral, we'd get 2 pi times the radius, and the radius is the distance from the axis of rotation over to our position x, so that's x minus negative 2, so that's x plus 2, times the height. And the height of one of these line segments is just the top function minus the bottom function. And that's pretty easy to write down. The top function is the weird one. That's 2x over 1 plus x cubed, minus the bottom function, and that's just x, dx. So for this example, we really didn't have any choice about whether to use washers or shells. Washers was just never going to work, and we had to use shells. So any particular example of a volume integral of rotation like this that you run into, you should think about slicing it both ways. Sometimes both will be a genuine option, and you can choose washers or shells, but sometimes only one way or the other is really practical.